Okay, so I will just go through the slides quickly, and then more focus a lot more of the time on the exercises that I really just skipped over pretty much last time. So to start off with, we will go through this first set of slides, the introduction to R slides, and just the basic functions. Let me make this full screen. So this was just talking about when we introduce R, the basic sort of mathematical operations, making sure that we complete the operation before we press enter. Otherwise, we'll get this sort of hanging command. The use of parentheses and character strings that we need to use quotations, and use of comment symbols here with the hash and the spacings, and yeah, the use of the semicolon if we want to. Sometimes, I mean, we don't use it too much, but sometimes we see people use it online a bit. You might put two R commands on one line and separate them with semicolons. So this was the first exercise. So what I'll do on all of these exercises, I'm going to switch into the R Studio, and then I'll open the solutions and just go through and explain the answers. So these first few ones are going to be pretty quick because they're all fairly simple. Maybe I can make it a bit bigger. I'm not sure if this is maybe a bit easier to see like this. Okay, so the first one was just remember, just simple additions, right? So 5 plus 6. Remember, we can press Control Enter and run the code. So question 2 was fairly simple. Question 3, we can use the hash for the division. And this is just a simple subtraction. Okay, we want to raise to the power of anything. So if we want to do a square or cube, or here we raise to the power of 10, and we can use this kind of a hat symbol. So then we get this larger number up here. And then if we want to type our name, like use a label in R, then we can use the quotations. So here I just type my name. You could type whatever name you like. And then 7 was just asking a question: which symbol do we use to ignore code after, which is the hashtag, right? So just to demonstrate that, if we do 5 plus 6, we get 11. And then I press up to re-get the previous command, and then I put a hash inside. And you see we ignore everything after the hash, so we just get whatever we put in, we get back if we're not adding it. And then so the last question was just talking about how do we put two commands on one line. So that was using the semicolon here. So if we put our cursor at the end of the line, press Control, let's even do it visually, press the run button, and you can see it's as if we've entered it in, as if we've hit the enter button where the semicolon stands. Okay, so it's a fairly quick introductory exercise just to get some basic practice, that first exercise. In the second part of the slides, or the next part of the slides, we were talking about the functions, general format of functions. And in particular, we looked at how you can look at the help using the question mark to find out what the argument names are. And then we can use the tab key to auto-complete the typing of the function names and the tabs. And yeah, and what the defaults might be. And then we don't need to write the argument names in here, so we get the same answers out without writing x equals. But it's always nice to sort of write the argument names out just so it's clear when you're reading your code later. And then just some basic mathematical functions that are in the base package of R. So just to get some practice on how to use them. This was the next exercise, right? Using these functions in this table, having a look at the help file each time, seeing what the inputs are, what the argument names are, and then running them. We flick back to RStudio, open the second exercise here. So for the logarithm of 5, you can just write log x is equal to 5 and run the answer. The square root, we can use the sqrt function and then put the number that we want to square root. Here we want to take the absolute value of 10 and minus 11. So here we can write two functions. We can write absolute x equals 10, absolute x is equal to minus 11. Another way we could do as well, we could form a vector. We'll come to this later, but we could do 10 comma minus 11. We'll get the two answers out in sort of we've given two inputs here, so we get two answers out, a vector of length 2 here. Okay, the factorial function is useful if you need to do these sort of more complicated mathematical operations. So the factorial of 8 is 8 times 7 times 6 times by 4, so on, down to 1. So we can use the factorial function. It will do that multiplication for us. It can be useful when you're writing more complex statistical functions. And then question 5 was to round pi to 3 decimal places. So this was practice using the round function. So in R, there is an object already called pi. So when we type pi, and it's because it has this it's a very special mathematical number, R automatically stores pi to many decimal places. But by default, in R, it's only printing it to 6 decimal places. And if we wanted to round it to 3 decimal places, then we could use the round function and give pi, the object pi, which stores the value to many hundreds of decimal places. And we can round it to 3 digits using the digits argument. So we get the value here. And we could have just typed it as well here. This is another alternative, right, where we just type it to 6 or 4 decimal places and it will round. So question 6 was looking at the logarithm of 100 using the base 10. So there's a couple of ways of doing that as well. So we can use the log 10 function, which by default uses the base 10, and then we get the result. But we could have also done use the log function, put x is equal to 100 again, and put the base, rather than it being to the exp to the power of 1, we could put the log to the base 10, and we're going to get the same answers there. Okay, and then question 7 was the exponential of 4, so we can use the exp function. Printing your name, we can use the message function to do that. Okay, and you can see I print it to a different color when you use message. There's a print function in R as well we can use. See, it gives a slightly different output. It actually outputs a vector where it's got a kind of counter of how many objects are returned. I think there's one called cap as well that sometimes people use, which gives it a slightly different color. I like to use message a lot because it's simpler and it's a different color. So that's usually when you're writing your own functions, you might want to include a message in there to sort of tell the progress of how the function is running. Okay, so that was exercise 2. And then we talked about the logic operators in the slides. So less than and greater than, and less than and equal, and greater than equal. And then testing if something is equal or not equal. And then the and or operators. Again, everything here was going to be returning true or falses, depending on the operations. Okay, so then let's look at the third exercise, which was practicing with these operations. So here we want to test if 3 is larger than pi, so we can use the 3 and then the greater than symbol, and then we can use pi, the object pi. So here we see it's false. And here we can test if pi is equal to this 3.141593. So this again is false because pi goes to many decimal places in R. So this is why it's true to 6 decimal places, but in fact this pi goes to a lot more detail than these 6 decimal places here. Okay, question 3 was to test if 7 divided by 3, so if we just run that on its own, is 2.33, is less than or equal to 3. So that's true, right? That's 2.33 is less than 3. And then question 4 is, let's make this a bit bigger here. Question 4 was to test if 5 times by 2, which is 10, is greater than or equal to 10. So that's going to be true. So just practice in 3 and 4 with the less than, equals, and greater than equals. And then the next question, question 5, was to see if 1 plus 5 is not equal to 7. So that's essentially right. 6 is not equal to 7, which is true. And then question 6 was to test if the logarithm of 1,000, here we see it's 6.9. This is greater than 7. So we get a false out here, right? And the most complicated ones, question 7s and 8, which are using the and the or. So remember, and is, it needs, for that to return a true, it needs both statements to be true. Okay, so here we've got pi greater than 3 and pi greater than 4. So one is true and one is false. So when we do them both together, then we get a false because not both of them are true. Whereas or is a bit more relaxed. So if we're looking for just whether one of them is true. So it's pi less than 3 was pi less than 4. So we know pi is less than 4. So when we ask if pi is less than 3 or pi is less than 4, then we get a true back because of this second part. Okay. So next part of the slides, we were talking about the assignments. So how to sort of save these little objects in R using the arrow button here, arrow symbol. Yeah. And then we should be careful when we're saving, when we're creating, when we're assigning values to objects and the name that we assign them to, because we can end up overwriting functions already there. I'm not overriding them, but it can become complicated if we choose names that are already existing objects in R. And just noting here that objects are case sensitive, so yeah, we need to be careful with the cases. And then once we've got objects, we can manipulate them and build further objects on them to build up a sort of bit more complicated workflow. And here we can just, this is for listing which objects we've created, which is also in the RStudio as well, in the Object Explorer in the top right. And here how we can remove objects if we want to delete them straight away in R. Okay, and then the next part was talking about vectors. So here we're just creating a vector using the concatenate function, the C function here. And one's of some integers here. This one's with some character strings. And then we're combining them in these later on vectors. And here using the colons or the sequence function to create longer objects, longer vectors without having to type out all the individual components, and the sequence function here as well. We're using the length out argument, and finally the repeat function. Using here we see the difference between the times and the each. So the each is we are sort of scrolling through and then repeating each of the elements individually. And then we talked about how we can use these vectors, and R is very powerful when it's working with vectors, that we can apply functions that we've already looked at to the whole of the vector, rather than just working with an individual one number that we had been doing before. So here we could square it, add them together, or take the log. Okay, so this fourth exercise was really working with vectors. So let's go through the solution for the fourth one. So here we want to create a vector called A1 that takes the numbers 1, 4, 9, 16, and 25. So we can use the concatenate function to do this. Create the A1, and you can see it appears up here in our environment. And then if we want to print it out to the console as well, we can just highlight it and press Control Enter. A2, we're going to create a second vector that goes from 1 to 100. So we can use the colon operator to do that, and we can save it. So here we get the second object, A2. And let's type it out here as well, A2. So we can see it's the number 1 to 100. And then A3 was practiced using the sequence function. So we wanted to go from -8 to 20 in steps of 4. So we can use the by argument is equal to 4. And then run this. And then let's just check what it is by typing it to the console. So you can see this is the vector that we were sort of describing in the question. Then A4 was a vector that combines A1 and A3. Remember, A1 was these 5 numbers, and A3 was the numbers above. So when we combine them, we get the sort of combination of the two sort of glued together. Okay, and question 5 was the final creation of the vectors using the repeat function, where we wanted to repeat your first name and your last name. So here I just use my name, but you could use your name. And then we want to repeat each of them, each element 3 times. So we've got a vector of 2, length 2 for the first name and second name. And then we want to repeat it 3 times. So it'll come out with a vector of length 6. When we use the repeat. Oh, a 5 even. Okay, so then we can see they've repeated 3 times this vector of the first and second name. Okay, and then the second part was just the sixth question was to use some functions on these objects. So we had the a1 vector, and then we're going to use the square root function to work out the square root of each element of the a1 vector there. And in question 7, we wanted to test whether which of the elements were positive. So we can use a logical operator with the greater than 0 here. So we use it. Okay. So here we can run this to see which of them are greater than 0, and it will go through individually to see. We can see -8 and -4 are greater, not greater than 0, so we get the falses. And 0 is not less than 0, is not greater than 0, right? It's equal to 0, so we get the false. And then the remaining, what are they? Five elements are all greater than 0, so that's why we get the trues here. Okay, and then this last part might be slightly confusing, so it's important to go through. So here we have the A2 object, right, which is the numbers 1 to 100, and we're going to divide by A1, which is only 5 objects. Okay, so what happens when we run this code, A2 divided by A1? So what is happening is we've got the numbers 1 to 100, and then we're dividing by 1, then we're dividing by 4, then we're dividing by 9, then we're dividing by 16, and then we're dividing by 25. So if you imagine this is the number 1 divided by 1, 2 divided by 4, 3 divided by 9, then 4 divided by 16, 5 divided by 25. And then what happens with R? It recycles. So when we get to the number 6, it divides by 1 again. When we get to 7, it divides by 4, 8 divided by 9, 10 divided by 16, and 9 divided by 16, and 10 divided by 25. And then again it recycles, so it'll be 11 divided by 1. So this is why we get these sort of common patterns going through when we do A2 divided by A1. So it's taking this A1 and then creating, going through the A2 and dividing the first 5 by these numbers 1, 4, 9, 16, and 25, and then takes the 6 to 10, and then again does the same divisions, and then 11 to 15, and again the same divisions. It just keeps recycling what is happening. So when we do A2 again, which is 1 to 100, and we divide by A3, so this time A3 is not five numbers, it's, what is it, 1, 2, 3, yeah, it's 7 numbers. So when we do A2 divided by A3, we see we get this warning message. So what is happening here? So if we go to the top, we see we've taken A2, which was 1, the number 1, and we've divided by -8. And we've taken number 2, and we've divided by -4. And we've taken number 3 and divided by 0, which is where we get the infinity. And we take the number 4 and divide by 4, which is where we get the 1. And 8 divided by, number 5 divided by 8, and so on. We keep on going through, and you can see each time, just like before, we were recycling. But we get this warning message at the end, and that is because you see here we've got, for example, the infinity, right? So this is for the number 99, right? So for the number 99, we divided by 0, and we've got infinity. And for the 100, we've divided by 4, which gets to 25. And this warning message is telling us that when we've got to the number, we haven't sort of used up the whole of the A3 that we're dividing by, that they are not a multiple of well, A3 is not a multiple of A2. So it means that this recycling is not working like perfectly in sync as it did before. So in this first example, we did A2 divided by A1, we didn't get the warning message. So A2 was of length 100. A1 is of length 5. So 100 in 5 into 100 goes without a remainder. But when we do A2 divided by A3, we've got 100 divided by 8, which leaves the remainder. And this is essentially what the warning message is telling us. It still does the calculation. So it's not an error message, just a warning message telling us that it's not working like perfectly in sync, and that you need to be aware of that. And is that a problem? Maybe you need to check if it is. Okay, so that was exercise 4. Okay, so after that, back in the slides, we talked about some other functions that work with vectors. So these were just different sort of, what would we say, maybe, yeah, mathematical operations or mathematical summaries of the of vectors. And also if we want to maybe manipulate the vectors, maybe sort them or reverse them, or detect parts of the vectors that might be above or below a certain number, for example. And or if you want to create a crosstab based on a vector, if we just want to get the unique values. So here we're just showing some examples, and then in exercise 5 we were having some practice with them. So let's open up the solutions. So this was using the vectors that we just created in this previous exercise. So so we could use them to experiment with the or practice with the functions from the slides. So we've got the A1 vector again. And if we want to find the sum of all the elements, and we can use the sum function. In A4, if we wanted to find the maximum value, then we can use the max function. If we want to multiply all the elements together of A2, and we can use the product function. So you see we get this very big number, right? This is 157 digits to it before it gets to 0. So it's using this mathematical notation with the E there. Okay, when we got A5 and we want to find how long it is, then we can use the length function. So this is telling us that we've got 6 objects, 6 elements in the vector there. And A2, which was 1 to 100, we want to reverse it, we can use the REV function. And then question 6 was which elements of A1 are greater than 10? So we've got A1, we want to see which ones are greater than 10. And so what which provides is the number of the element where the logical function that's passed to it is true. So this 4 and 5 is really saying the 4th and the 5th part of A1. So this is the 1st, 2nd, 3rd. The 4th and the 5th part are greater than 10. So that's why we get the 4 and 5 out. So this can be really sort of a useful little function when you're creating your own functions, perhaps, or you're just searching in your database. Okay, and the range. Let's see what A4 was. Was this combined vector? And we can find the range. So it gives the 2 values back: the minimum value and the maximum value. And then unique is stripping away from here any repeated values. So it kind of keeps the original order, but as soon as it hits a repeat, like this 4, it will drop it because we've already had 4 before. And then we can sort the values if we like using the sort function. So by default, this is going to go from the smallest to the largest. But we can put decreasing is equal to false. Oh, maybe decreasing by falses must be the default. So we can change the default to true, and then we get the other way around for the sort. And then the table function. So remember, this was A4. When we do table, we get on the first kind of row is like a column name. So they're sort of telling us each of the values in A4, and then the second part is telling us how many are being observed. So it's like a tabulation. So we've got two 4 values, 2 16 values, and 1 20, 25, and all the other values. There's only one observation. Okay, so the question 11 was working with if-else. So this can be really useful when you're creating categorical data from a data frame, from a numerical value. So we've got this vector A4, and we want to recode it to give the value 1 if it's positive. So if A4 is greater than 0, and 0 if it's not. So we can use this sort of logical expression, and we can summarize it rather than giving out trues and falses. We can recode it to 1s and 0s by using the if-else. So this is the test, whether A4 is greater than 0. If it's true, then it returns a 1. If it's not true, it returns a 0. Okay, and this is just very similar, where rather than returning a 1 and 0, we're going to return a label, positive and negative, or 0 if it's less than 0. Okay, so again we get out the same length vector, but in this case they're character strings rather than numbers. Okay, so that's exercise 1.5. So let's go back to the slides, just skip through. So after that, we talked about some more statistical functions rather than mathematical. So these kind of mean, median, summary, for example. Talked about taking samples using the sample function in R, with and without replacement. Generating random numbers just from some sort of more basic probability distributions from the normal, binomial, Poisson, and uniform distribution. And then we got onto the exercise. So let's go back to the R Studio and open up 1.6. So the first part was to create a sequence of numbers from 1 to 25 that has a length of 8. So we can use this length out argument. This just means we're going to get only 8, a vector of length 8 out of it. Right? So it calculates these steps going between 1 and 25, equal steps between 1 and 8. If we want to find the mean of that, then we can just use the mean function. If we want to find the standard deviation, we can use the SD. Okay, in question 4, we wanted to create a sample of size 8 from a sequence of integers between 1 and 100. So we're going to pass to x the numbers 1 to 100, and then we're going to take a sample of them, and we're going to want to select 8 random numbers from that. So I'm going to get out A7, and then I get these 8 random numbers. So this will be different when you run it on your computer than from my computer. Or if I run it again, you'll see I'm going to get out some different numbers, right? So it's not always, well, I got 2 again, but that's just random. So you can see we every time we run it, we're going to get a different sample. So it's all being run on your specific computer. So you're going to return different values out because we're all using different computers. Okay, so then we've got A6 and A7, and question 5 was asking for the correlation between the two. So in my case, with my A6 that I just created, the correlation is minus 0.22. But I guess your answers will be different because you'll have a different A7 that you've created from the sample function. Okay, and then question 6 was to create another object, A8, where we want to generate 8 numbers from a normal distribution with a mean 10 and a standard deviation 2. So here we can run it, and you can see we get these numbers roughly around 10, yeah, which is the mean value, and then you can see they deviate by well, they have a standard deviation of 2 here. So again, when you run it on your computer, you'll get different results because it's a random generating function here, rnorm. So if I run it again, for example, again, that's a different set of numbers. They are essentially coming from the same distribution, but just because they're random, we're getting different values out. So for question 7 and 8, we can use to find the interquartile range, which is 3.46 for this A8 that I just created. And then we can use the summary function, which gives us the minimum, the maximum, the first and the third quartiles, and the mean and the median. So summary is a very nice function, but it saves you typing mean and SD and median, for example, or range. So it sort of has a quick summary there for you for each of the values in there. Okay, so that was exercise 1.6. And then we started to talk about objects after this. And that everything in R is an object, including these objects that we create using the assignment, the functions that we create, that there's already some objects in R that are stored, like pi that we talked about, or letters. And there's different types of objects, right? So we had vectors, matrices, here we've got data frames, and here we've got lists. And lists, for example, are used quite commonly in R for sort of non-simple operations. So for example, here we run a regression model, and what we get back is really a list when we save the regression model. We can look up using the list different parts of the regression model. So we talked about objects and the different types of objects, and we just talked briefly about those 3-4 different types of objects. And of course, there's many different types of objects in R, but those are sort of the four most basic ones. And then within objects, we have different modes. So this is like the modes of the data. So whether we're dealing with integers, whether we're dealing with character strings, or numeric data, or logical data. So just some basic types of modes. And then we talked about indexing, how we can select different parts of an object. So here, when we're using a vector, we can use the square brackets and put the number, like the location of the part of the object that we want. So here we want the third part, or here we want the first, the third, and the fourth part. And that we can drop parts of the vector, or we can replace parts of the vectors using the assignment. And again, with matrices, we need 2 dimensions to index different parts of the elements. And with a data frame, we can use the not only the indexing on the rows and the columns, but we can also use the row and column names if the data frame has it. Or we can also use the dollar notation to select a given column. So we can use the data frame name, dollar, the column name. And we can also use the dollar notation with lists, where we can get the object, then the dollar, and then the element of the list that we want to look at. And with lists, we can use double square brackets as well as an alternative to using the dollar notation. And then finally, before the exercise, we talked about missing values. So in R, we use NA to denote missing values. And whether we have NAs or not in the data might give us different outputs to the data, where the function might not return a value, or it will return an NA if there is a missing value in the original object. So for example, summary works fine, but we just get this extra column of NAs. Whereas with the max function, we will get an NA out unless we set NA.rm, remove the NAs to true. Okay, so then we went to exercise 7, shows a bit of practice with these different types of objects in different modes. So here we created a matrix, M1. Go print that out. You can see the entire matrix here that we've created, and we've just filled it with numbers 1 to 28. And then here we want to print out the second row. So here we can use the square brackets to say we want to select a part of the object, and we can say we want the second row, so we can put 2 comma there. So say remember, the rows come first, then the columns after the comma. So we can get the second row, which is this element here, right? The 2, 6, 10, 14, and so on. Okay, if we want to print out the top right value, then we can think about that. The top right value, so it's going to be in the 7th column if it's on the right, and if it's on the top, it's going to be in the first column. So it's going to be M1 square brackets 1 comma 7. It should give us the number 25 out there. Yeah. So we can pick a specific cell out from the matrix. And if we just want a column, then we can say we want we just use the square brackets again, and then say comma without anything in the row, that we want to take all the row, and then we want to take the first column. So we take every row of the first column, gives us this 1, 2, 3, 4, this part here. Okay, so that was dealing with the matrix, and then the next parts of the questions was dealing with this Swiss data frame, which one we see we printed out here is a kind of default data frame. A data frame that's already stored in R. That's a sort of a toy data frame. It's based on different parts of Switzerland. So we want to print out, we'll select a column from this data frame. We can use the dollar notation, or we can use the square brackets, and then just like we did here, comma, and then the number of the column or the name of the column. But, here we're going to use the dollar. So to get the infant mortality rate, we can run this and it will print out just the infant mortality column, which is this last column here. You see we've got this 19.3, 18.2, and so on. Scroll up, you see infant mortality. In fact, maybe I should just show this. Okay, I can do this here, maybe. Okay, so we can use the tab key here. So I'm pressing tab, and then I press dollar, and then it comes up already in RStudio that we can select. So I can just go press up and down. I'm going to press enter, and it's selected it. And so we can avoid making typos on misspelling the column name just by using the tab key to auto suggest. So we can do Swiss. Oh, what did I do? Swiss dollar, and then it's already come up. I didn't even need to press tab. Okay, so then question 5 was to find the maximum fertility in the Swiss data. So we can use the max function and then give the column that we're interested in finding the maximum value at. So here's all the fertility data, and we can find the maximum value using the max function. And here we're question 6. We want to select a particular region, this Glane region, and a particular value for the Catholic. Right? So if we look at the Swiss data again, okay, you see we've got all the row names here, and then we've got the column names at the top. And so what we're doing is selecting this Glane, and I'm not even sure where that is. Yeah, so we could look up the number and try and pick it out. So here we could try and count that this is what 1, 2, 3, 4, 5, 6, 7, the 8th value. So we could say 8. We say Swiss square brackets 8, comma Catholic is what 1, 2, 3, 4, 5. And then we could get the value out that way, or we can use the column names and save ourselves looking up the particular value. So here we get the 97.16, which is, where is that back here? 97.16. So it's this value here, right? So we can use the names when we're working with data frames. Okay, then the last 2 questions were working with this A8 object that we created earlier in the previous exercise. So here we want to set the 3rd and the 6th part, so this part, and 3rd, 4th, 5, 6th part, we want to set them to NA. So we can use the assignment and then say that they're NA. So here you see we replace the values with NAs, and we want to find the variance of the remaining numbers. So if we just did var A8, we get an NA out, but we can use the NA.rm to ignore these NAs and give the variance of the remaining values in the data in the vector. Sorry. Okay. So the last, last parts of the first set of slides was talking about functions, talking about how R is a programming language, and we can create our own functions by using this function called function. And that there's arguments that sort of telling us about the different inputs that we can go in. Then we can have a lot of code that can provide various actions, and then we can return values out of this. So here was just an example where I was creating a function called mySquare, where we would take a value of x, and then it would square it, save it as y, and then return the value y. So we could give it different values of x. And here we wrote a more general function where we can call it myPower, where we can again give it any value of x and any value of p, but the default value for p here is 2. For x, there's no default value. And then we can use it to return the calculation. So that was a basic function. And then we talked about for loops for doing repetitive actions. So for here, for example, we created a vector that was just 12 empty numbers. And then we did a for loop where for 10, we went through this set of code 10 times. So these 3 lines of codes code, we went through it 10 times, where in the first step, we would generate one random number from a Poisson distribution with the mean depending on I, where I changed the value in each step of the loop. So first off, it was the value 1, then 2, then 3, then 4, up to 10. And we printed the value out, the random number that we calculated, and then we filled in this V8, the value that the random number took. So in the first case, it generated a random number called 4. So it saved it as X, and then it printed it out using the message function, and then it replaced the V8 in the first part, because I was 1, with the value 4. That was the random number generated. So this is why this became 4. And then the second part of the loop, the random number that was generated with the lambda is equal to 2 was 0. So it's filled in there, and so on. See, as we get higher, as we get to the 10th value, the numbers get a bit higher as we're increasing the lambda, the mean of the Poisson distribution. And the numbers are getting higher. And the 11th and 12th elements are not filled in because we only ran this loop between 1 and 10. Okay, I'm just showing some more examples. Here we're creating a projection where we're using a base population, and then we're projecting it based on a growth rate of 0.05 using sort of a simple demographic model, very simple demographic model. We can wrap this in a code into a function where we can take any sort of starting population, any growth rate, and we can run it for however many steps ahead in the future we want to run. Okay, so this last exercise was easily like the most complicated one out of the ones that we've gone through so far. So yeah, I find it's often a bit of a struggle, especially when you're starting off. But if you remember, maybe let's just show it in the exercises. I sort of gave you a template in the actual question. So this was the exercise, and this is the solutions, where we just had to fill in these blank parts that were not explained. Okay, so following the instructions, we wanted to create a function called TFR. So this is already written for us, right? We have the TFR. It's going to be the name of the function. And we're creating a function, so we use the function called function to do that. So this is why we write function here. And then we wanted to have argument names ASFR. So then we can call this the first argument is going to be called ASFR, and the second argument is going to be called period. And the default value for ASFR is null, and the default value for period is 5. And we're going to want to do the calculation for the TFR, which is going to be the period times by the sum of the ASFR. So we can run this, and then we can see at the bottom here, we get this TFR function that we can use to run it on various sets of data. So for example, imagine we had age-specific fertility rates for those. So for example, this could be for between 15 and 20, 20 to 20 to 25, 25 to 30, and so on, between different ages of females. And we have the first set of age-specific fertility rates. We get a TFR of 2.3. For the second set, we get a TFR of 3.6. Okay, so it's just quite basic illustration of how we can create our own function in R. There's not really a TFR function, at least in these base packages in R that's loaded when you download R, and we can do our own calculations for that rather than having to retype the code every time. Okay, question 3 was another example of creating a function. Let's go back to the question so we can see what we needed to fill in. Where we need to create a function called rPoisAdd with n with the default value of 10. So we can see that's already done. And we're going to have 2 inputs, one called lambda1 and another one called lambda2. And then for each of them, we wanted to generate a random Poisson values based on whatever n was and whatever the lambda1 and lambda2 was. And then we want to return the sum of them. So here, this is it filled in, right? So the name of the function is rPoisAdd. This is what it asked for in the question. We're creating a function, so we use the function. We need to type function, and then we need to say what our inputs are going to be, which are going to be n, lambda1, and lambda2. the default value for n is 10, the default value for lambda 1 and 2 is none. And then we're going to have some actions within this function. So we're going to create an object R1. It's going to be generating whatever the n was. So in this, the default example is 10. So we're going to get 10 random Poisson numbers with a lambda with a mean value, depending on whatever's given to lambda 1. In the second row here, we're going to create this R2 object, which again is going to be taking 10 objects by default, 10 objects, 10. Going to create 10 numbers, but it's going to take a different mean this time, depending on whatever lambda 2 is. And we're going to return the summation of R1 and R2. Okay, so here we're going to run it first we need to run the function code. So it goes into the, creates the object, and then we're going to run it based on n is equal to 20, and then with lambda 1 is equal to 5, and lambda 2 is equal to 8. So we can play around with this, right? So let's just do it with 2. Well, let's do it with 2000. Okay, and we're going to get 2000 values back. Or we could do it with, let's say, 8. Again, let's say change the lambda 2 to 80, for example, and we're going to get much higher numbers, right? We've changed what's going into the second line of the code here. Okay, question 5 was using this, creating a function called gauge. So this is based on a demographer gauge, who sort of, how would we say, he proposed this equation to calculate fertility age schedules given a kind of age range, given a constant, and given the minimum mother's age and the width of the mother's age. So this is the equation that needs to be calculated, and we want to have a sort of a flexible function where we can change these inputs, right? We can change the constant value, we can change the mother's age, we can change the minimum mother's age, and we can change the width of the mother's infertility age. So be the basis of the calculation of y. So y is going to be equal to c times by x minus s times by s plus w minus x to the power of 2. And then we can return the y value in there. Okay, so let's go back here. Yeah, here we go. So we've just essentially copied and pasted that equation in here. And then we've set the defaults for the age range of, this is of fertility ages between 15 and 55. And we set the constant to this strange number. That's sort of what Gage sort of proposed when he was writing the function. Proposing this equation here. Okay, so what is going on here? We've run the code, so now we've got this gauge function, and now we can experiment with it by running it on different sets of values. So in this first case, we're going to save the objects as y1. It's going to be gauge when it's run with its default values. So this is when x is between 15 and 55. And c is equal to this equation here. So what's returned is a set of 41 values, which are going to be sort of age-specific fertility rates based on this sort of smooth curve that Gage was proposing. And we run it again, but changing the values. So again, doing the calculations, but changing the age range between 15 and 60. And changing the constant to 1 divided by, what is this, 400,000. And so we get some different values out. And then we just wanted to uncomment the code here just to do a plot. So here we can see we've got plots, and you can imagine these are meant to be then age-specific fertility rates for different ages. So remember, age starts at 15, right? So this is the 15th observation. So you can imagine this is really like at age 25, and this is at age 35, 45, and 55. So this is talking about the index, right? So this is the, it's not an age per se plotted on the axis scale here. But you can see this gauge function, it's giving different curves based on the different inputs that we are giving to the data. Okay, so that's essentially exercise 1.8, which is, like I said, one of the more complicated ones, and perhaps not easy to really follow or go through right at the start of learning R, but I think I always want to like include it in the course just so you can see the power of R in creating functions, and that at least you could see, for example, with this TFR example, that you can really save yourself writing a lot of code by creating a function. So rather than, if I had like 10 different sets of age-specific fertility rates, so here we only had 2, but imagine we had like 10 or 50 different regions and we wanted to calculate the TFR, then it makes more sense to write this TFR function. And then we can just write TFR and then whatever the vector is, right? Rather than writing out period times by the sum of ASFR and doing this 50 times, writing this equation. Here we only have to write TFR once and give it the different values. Okay, so that was essentially the end of that set of slides. So I think that's probably a good time to take a break, and then we can go on to the next exercises in the next set of slides when we come back. So I think it was a 10-minute break. So maybe we come back at 5 past, well, in 10 minutes, let's say.